Good day, viewers, and welcome to my physics class. I am Ms. Cham, taking you through, and the topics that I'll be dealing with today are as follows. We'll be dealing with forces in 2 dimensions, and it falls under, Newton's second laws will be covered. We'll also talk about inclined planes. We'll also talk about how to resolve forces into their components and state the conditions necessary for a body to be in a static equilibrium. First of all, I will have to recap with you, or I will have to recap like how to resolve forces into 2 dimensions. Because when we talk about forces, we all know forces are vector quantities, and all vector quantities have magnitude and direction. The same thing applies to forces, and they also have 2 components. The components are the x and y components. So all forces will also have a vector. They are also a vector, and this means they have a magnitude and also the direction. When we talk about the direction, we first of all have to resolve it into x and y components. And in doing so, we have to know that the forces will be inclined at an angle theta. Now, this is the magnitude of the force, that's F, and this gives us the Fy component, and this will be the x component of that force. In resolving this, you have 2 options. You can obtain 2 triangles from this. You can use the one that has an angle of theta inclined with the horizontal, or you just have to extract this triangle which has an angle theta. So that's the simplest. So we're going with that, and this will be something like this. We have the magnitude of F, and this will be F of y and F of x, and this gives us theta. If you recall, when we studied vectors, we said vectors also have 2 components, and the x component will be obtained by using, we will use sine of this theta, and that will give us, the sine will be opposite all over the hypotenuse. Since we're using theta, the opposite side will be Fy, and the hypotenuse will be the magnitude of F. So when we simplify this, it becomes F of y is equivalent to the magnitude of the force times the sine theta of the angle. And the same thing applies when we use cos theta. It becomes the adjacent side all over the hypotenuse. And looking at the angle, the adjacent will obviously be Fx, the hypotenuse will be F. If we resolve this or we simplify it, we will obtain something like F of x, which is equivalent to the magnitude of the force times the cosine of the angle theta. So whenever you resolve vectors or forces, this is what you do. The vertical component will be F sine theta, and the horizontal component will be F sine theta, where F gives the magnitude of the force and theta will be the angle inclined at the horizontal or at the vertical, depending on what triangle you've used. I think that's a good recap. And then we're moving into solving forces into components. We moving? Okay. Now, if you look at what is being displayed on the ball, you are given an object which is being dragged, but then the force applied is not horizontal or vertical. All we know is that it is inclined at an angle. So to go ahead with this type of problem, you have to treat forces as vectors. And this will be done by creating something like this. We'll have to draw a free body diagram, which you will get to know at the end of the day. This is what was given, an object which is being pulled with an angle, with a force of F. But we are not told if the force is vertical or horizontal. But by observation, we will know that the force is inclined at an angle theta. Now, to obtain the angle, you have to use a different color to be able to see where the angle falls. And this is done by drawing a triangle like what we did previously. And this will give us F of x, and this will be the magnitude of the applied force, and this side gives us Fy. But since this is a box of mass m, we know that it is resting on a surface which is horizontal, and then we are told that the surface is smooth. All we do is to identify the forces acting on the box that rests on the, horizontal surface will have 2 forces acting on it. The first force will be the normal force and the gravitational force, G. But then if you look at the other side of the diagram, there is an applied force F, which is inclined at an angle theta. And if we resolve it, we will notice that there is a magnitude of Fy which points vertically upwards. So that force has to be added to the normal force And that should be something like this. The dot will represent my mass, m. We have the normal force acting. We also have the force of gravity acting. We are still looking at the diagram as our reference. There is a force which is horizontal, and that force is given as F of x. It is obtained when that force was resolved. The moment you resolve it into x and y, the magnitude of F will totally disappear. It wouldn't appear again, and the remaining force we have will be Fy, which will be added to the magnitude of the normal force. And this will be Fy. That's the first step that we did. Now step 2 will include, calculating the magnitudes of F and X, Fy and F of x. And if you recall, we obtained them as follows. Fx equals to F cos theta and Fy equals to F sin theta. So if we want to know the total forces acting, we will just divide this into two components, the x and y forces. This is dynamics in 2 dimensions, so we'll be dealing with both x and y axes all together. If you recall in your SS1 or grade 10, we dealt with dynamics, but then in that case, we dealt with x or y axis only. But since this is 2-dimensional forces, we'll be dealing with x and y forces all together. Now that's the first thing you did. For simplicity, you will be dealing with the x components first, then you deal with the y components. And this is going to be, we divide the forces into their components, and that is going to be the sum of forces in the x direction, and this will be the sum of forces in the y direction. And we are told that the force is accelerating towards the right. That's the direction of acceleration. So it means the object's acceleration along the y will be 0. And the other thing I wanted to mention is that an object cannot be accelerating along x and y at the same time. You either take the acceleration to be on the y-axis or on the x-axis, but then you cannot give an object an acceleration in both directions. So in this case, I'm going to use the acceleration to be that which is present on the x-axis, and a of y will be 0. Now we recall from Newton's laws that the sum of forces will be equals to ma, and this gives us the forces along the x, because this is labeled as f of x. So this gives us, if you look at my diagram, there is only one force acting on the x-axis, which is f of x. So I will write f of x, which is equivalent to ma of x. But then which force is on the x-axis? Is fx, and fx is given as f cosine of theta. Therefore, f of x will be ma of x. We substitute. In place of f of x, I will just write f cosine of theta, which is equivalent to ma of x. And that is it. If the acceleration is required, then we divide both sides by m, and this gives us a of x is equivalent to f cosine of theta all over m. And that's the magnitude of the force, or the magnitude of the acceleration. If the quantities of f, theta, and m are known, then the acceleration along the x-axis will be found by substituting the values into the equation. Then we move to the second part, which tells us that the sum of forces on the y-axis is equals to ma. Again, remember what I said, a of y will be 0, because then acceleration can be present in both x and y directions. And if you look at our diagram again, we will see something like Fn, upward will be positive, down will be negative, and to the right will be positive. And this gives us Fn minus mg. What other force is present? I think those are the only forces. No? How about Fy? It is also present, and it acts to the right or upward. So we give it a positive direction, which is equals to 0. Because m times 0 will always be 0. And this will be simplified as Fn is equivalent to mg minus f of y. If you recall, Fy was found as f applied sine theta. Then we substitute that into the equation, and this gives us the normal force is equivalent to mg minus f sine theta. I hope I've communicated. Now we move on to explaining what a free body diagram is. Now you saw me draw a free body diagram, and by now I suppose you know what a free body diagram is. It is just a vector diagram which shows the magnitude and direction of the forces. The length of the force will represent the magnitude, and the arrowhead attached to that length will indicate the direction of the force. If you look at my diagram, the normal force was acting vertically upwards. That is why the arrowhead was also drawn vertically upward. The mass of the force of gravity on the mass is acting vertically downwards. That was the reason why we said the mg will always point downwards. That's just a vector diagram or a free body diagram. Now we take a detailed example. Okay, now we are told that F, the applied force is, what's the magnitude of the applied force? Is given as 50 Newton, and the angle at which this was raised is 30 degrees. So we can substitute into the equation and obtain our variables. So the acceleration along the x-axis, what's the mass of the object? Let's say the mass is 5. The mass is 5 kilograms. So the acceleration will be F cos theta, where F is just 50 Newton times the cosine of 30 degree divided by the mass, which is 5. You just point this in your calculator and your answer must be expressed in meters per second squared. The same thing applies to the normal force. The normal force will be obtained as F normal is equivalent to mg. We know the magnitude of m to be 5. G on the earth's surface is 9.8 minus Fy, which is 50 sine 30. So the normal force on that object will be whatever you have, you just express it, because I don't have a calculator right now, and your answer must be in Newton, because all types of forces are measured in Newton, and normal force is also a type of force. Is that understood? Good. Now we move on. This problem that I gave included what? The calculation of acceleration and normal force. But then you can also be asked to resolve a force into its component. Like what we just did. If this was the force, we are told the force is just 50 Newton, the applied force, and the angle inclined at the horizontal is 30 Newton, or let me say 30 degrees. You might be asked to resolve the forces into its component. As I said earlier on, the components are f of x and f of y. And if we use Pythagoras theorem, we'll be able to obtain sine theta as the opposite side all over the hypotenuse. We are told the opposite side is fy and the hypotenuse is fx. Therefore, sine 30 will be equivalent to fy all over 50, and this gives us fy equals to 50 sine 30. And that will be your vertical component, or the vertical component of this force. The same thing applies. If we are required to solve for the horizontal component, we will do the same thing. We use the cosine of theta is equivalent to the adjacent side all over the hypotenuse. We are using this angle 30 degree, and by observation, the adjacent will be f of x. So cosine of 30 will be equivalent to the adjacent side, which is f of x all over the hypotenuse, which is the magnitude of the force 50. So this will simplify as f of x equals to 50 cosine of 30, and your answer must be in Newton. Good. Move on. It's covered. Okay. Now there's a problem given on the board. We are told that, a magnitude of 100 Newton acts on an object which is inclined at an angle of 45 degrees. And the question says, we calculate the magnitudes or the components of x and y. We're going to apply the same explanation I gave. You're given the magnitude of the force. That's the magnitude of the force, which is 100 Newton, and the angle it makes with the horizontal is 45 degrees. You have to identify your x and y components. This is the magnitude of the force. The hypotenuse, or the longest side of the triangle, will always give you the magnitude of the applied force. And then the vertical component, which we usually associate with the y-axis, will be the magnitude of the x component, and then the that will be the magnitude of the y component, and that of the x component will be given as the horizontal component. So we just use trigonometric ratios and the answers will be found. So from here we will see sine theta, which is equivalent to the opposite side, f of y all over the hypotenuse, which is just 100. And this simplifies to Fy equals to 100 sine 45, since the angle is given. Can you point to that? 100 sine 45. Sine 45 should be 70.71 Newton. So the x component or the y component will be 70.1 Newton, and therefore the fx component will be 100 cosine of 45. 100 cosine of 45. And that gives us 70.1. They are both approximately 71 Newton. So the x component is 71 Newton and the y component is 71 Newton. This is because sine 45 is equivalent to cosine of 45. Okay, you should be able to solve that on your own. Just give it a try, it's a challenge. Yeah, the same procedure is applied. Then we move on. We've already drawn the free body diagram. All we need to do is identify the forces that are acting on the vertical and horizontal forces. Now, these are the forces acting on the horizontal axis as shown on the diagram. But then you have to note that the acceleration on the y-axis is always 0. And when we apply Newton's second law, it tells us that the sum of forces must be equal to the product of mass times acceleration. And the sum of forces acting will be Fn plus Fy minus mg, which is equivalent to 0 since A is 0. And this gives us Fn is equivalent to m of g minus f of y, where f of y is given as f sine theta. Therefore, Fn becomes my minus f sine theta. Can we solve for Fn since all the variables are given? The mass is given, gravity is given. All of these variables are given. Let's just insert it into the equation, and this gives us 3 times 9.8 minus the applied force, which is 20 sine 37. So Fn becomes 3 times 9.8 minus 20 sine 37. And that's 17.17.336 Newton. That's the normal force acting on the object. So we shift our attention to the forces acting on the x-axis, and that gives us sum of forces on the x will be equivalent to mass times the acceleration on the x-axis. Now, as we said earlier on, this is a rough surface, so the forces acting will be on the horizontal will be f of x and the frictional force. So we take that again, and it will be f of x minus f of k is equivalent to ma of x, where f of k will be mu times Fn. And when that is solved, we will obtain something like 0.2 times 17.36. And that gives us the frictional force acting. 3.47 Newton. That's the frictional force. So we have f of x minus the frictional force, which is 3.47, is equivalent to the mass times the acceleration. And f of x is just f cosine of 37. And that will be 20 times the cosine of 37. 20 times the cosine of 37 gives us 15.97 Newton. So that gives us 15.97 minus 3.47 is equivalent to the mass, which is 3 times the acceleration, which is a. Now we make a the subject by dividing everything by 3. So the acceleration on the x-axis will be 15.97 minus 3.47, and that's 12.50. Divide by the mass 3, and that gives us 4.168 or 17 meters per second squared. That's the acceleration of the object on the horizontal axis, and it is shown there. If you want, you can use g to be 10 meters per second. Your answers will be the same.
Sorry, can you go back to that slide? The slide before this. Go.
Okay, it's the same problem. They're just taking you through. We've already answered that problem. And now let's look at the other problem here. Instead of the force being applied vertically up, it is not vertically up, it is not horizontally down. We don't even know the direction, but all we know is that the arrowhead points to the ground, and it means the applied force is vertically down or inclined at an angle. So we see what happens next. We will take the diagram again. We'll draw a free body diagram like we did with the previous problem and identify the forces that are acting. That's the mass. It is resting on a rough surface, and that tells us friction is present. The forces acting will be an applied force. That's the applied force. That's how the applied force is acting this time around. We have a normal force. We have a weight acting. We have an x-axis here, or f of x on the horizontal axis, and y vertically down. So if you observe, the first problem, y was acting vertically up, but in this case, the vertical component of the applied force is no longer vertically up, but vertically down. So that tells us that it is now supporting the mass of the object, or the force of gravity that is acting on the object. We will do the same thing as we did with the first one, and that includes drawing a free body diagram where the mass is just replaced with a dot, and that gives us the normal force, force of gravity mg, and Fy, which is also vertically down. This is F of y, and F of x is still on the positive x-axis, and friction will be on that direction. The object is expected to accelerate in the positive x-axis. Good. We will take the sum of forces, that is Newton's second law. F of y will be equivalent to ma of y, where ma of y will be 0, and the forces on the vertical are Fn, which is positive, minus mg minus f of y is also 0, and that gives us Fn is equivalent to my plus f of y, mg, sorry, plus f of y, and this gives us Fn equivalent to mg plus f times the sine of theta. We move to the x-axis, and that gives us sum of f in the x-axis will be equivalent to f of x minus f of friction, which is f sub k. That is all equivalent to mass times the acceleration in the x-axis. We know f of k to be mu times Fn, where Fn is mg plus f sine theta, and fk, or f of x, sorry, becomes f times the cosine of theta. So when all of these are, if the variables are given, we'll be able to solve for Fn. We'll also be able to solve for the acceleration. Now let's concentrate on the question and see what we have there. Yeah, it's the same question. The mass is the same. The mass is 3 kg. The coefficient of kinetic friction is 0.2. The applied force is still 20, and the angle of inclination is 37 degrees. So when we substitute this into the equation, Fn becomes 3 times 10. G is 10 meters per second squared, plus the F applied, which is 20 times the sine of 37. And that will be 30 plus 20 sine, 30 plus 20 times the sine of 37. And that gives us 42. F applied is 42 Newton. And F of x will be 20 times the cosine of 37. And that should be 15.97 Newton. Therefore, A of x will be equivalent to Fx minus Fk all over m. And this gives us Fx is 15.97 minus Fn times mu. Fn is 42 and mu is 0.2. So Fk will be 42 multiplied by 0.02, and that gives us Fk equals to 8.4 Newton. Therefore, the acceleration of this object will be 15.97 minus 8.4 all over 3. And that is, A is equivalent to 2.52 meters per second squared. Now, these are try questions for you. I'm not going to answer the question, but then I will just give the answer in case you want to try them at home. The correct option for this question is D. It is very similar to the one that I just explained the previous slide. In the previous slide, if you look at the diagram, you will just observe what's going on there. You compare it with what I have done so far. So this one should be good as well. So you are good. Those are try questions for you, and I wish you all the best in trying them. We move on to our next subtopic, which is inclined plane. And I believe we all know what an inclined plane is. We're not using it on the machines here, but then it can also be classified as a machine. It enables us to do our work with a very small distance or at a very fast rate. You all used it once or twice in your lives, so you should know what an inclined plane is. We move on. Now, in dealing with inclined planes, all you need to note is that the horizontal surface is already wiped off. We will no longer be dealing with a horizontal surface. That is a surface in which a normal force will always be equal to the force of gravity or to the weight. That is just true when the surface is horizontal and it has no angles or any inclined force acting. But with the inclined plane, you have to go at a different speed. We are going to do the same thing, and you will enjoy it, I believe. We move on. Now, you know what an inclined plane is. Whenever you are given a question that contains an inclined plane, the first thing you're supposed to do is to draw the plane. You have to draw the plane. You have to note the angle at which the plane is inclined at, and mostly it is inclined with the horizontal, that's angle theta. Then you have to understand that the force is no longer horizontal, but it is inclined at an angle. So you need to note the forces acting. When you deal with an inclined plane, there are two forces that will always be present. That is the normal force and the weight. That's the normal force, which is perpendicular to the plane. And that's the force of gravity, which is weight. But then the most important thing that students tend to forget is that weight is a vector quantity. And in this case, it has to be resolved into x and y components. In doing that, I wouldn't just waste time because it was already treated in the previous chapter. We will deal with that is always going to be the mg of x, and this will be the mg the mgy of the weight. Whenever a quantity is resolved into its component, the magnitude is no longer used. And the same thing applies to the weight here. We've resolved it into x and y components, so that tells us that the mg will obviously disappear. All you'll be dealing with will be mg of y and mg of x. Have I communicated? Good. And the second thing you need to note is that this angle theta will always be equivalent to the angle of this theta given. Theta is always equivalent to theta prime. That is if you have studied geometry. Good. Okay. Now we have different cases to deal with when it comes to the inclined plane. The first thing I want us to study is what an object sliding down an inclined plane with a constant speed. The object is sliding down, that's the direction of acceleration, but with a constant speed. Now if we recall from kinematics, we know that when an object moves at a constant speed, its acceleration will always be 0. So it means when an object slides with a constant speed, a of x will always be 0 meters per second squared, and a of y will also be 0 meters per second squared. Please note the condition. The condition is that the object might be at rest, or it is moving at a constant speed, or it is in equilibrium. When an object is in equilibrium, the acceleration will be 0. It will also move with a constant speed. Whenever you study inclined plane, you have to understand these 3 points that I just noted. Good. Now we have 3 scenarios too. You can have an object, two objects, one resting on the plane and the other will be connected to a string and whilst it is hanging. That is a special case. The other case is when the object is sliding at a constant speed, but then the surface is termed to be rough, and that tells us friction is present, or a smooth surface. If the surface is smooth, it means the mu of k will always be 0, and that tells us there is no friction present. The moment the magnitude of mu is given, you know the surface is rough, and friction must be present. Is that clear? Good. Let's go through the notes. That is what I was explaining. Now let's look at this case. You are told that in this case, the block can only accelerate along the surface of the plane. It can only slide down or upwards. I've explained all of those, so no need to repeat them. Let's just take the first case. Case 1, we'll be dealing with the first case, and this case tells us that the object slides with an acceleration ax along the x-axis, and the only force acting is just the magnitude of mg in the x direction. Good. Now we will deal with the forces on the y-axis, and this tells us the acceleration on the y will always be 0. And these are the forces acting, Fn minus mg of y, which is equivalent to ma of y, but we note that a of y is 0. So substituting this into the equation gives us Fn equivalent to mg cosine of theta. We are done with the y forces. Now we focus on the forces on the x-axis. If you look at my diagram, there is only a single force acting on the x-axis, which is this force I'm going to circle with my red pen. This is the only force acting on the object in the horizontal axis, and that force is called the mg of x. So we will apply Newton's law, which says the sum of forces, but unfortunately there is only one force. That would be mg of x is equivalent to ma of x. Good. Is equivalent to ma of x. And then ma of x, mg of x is given as mg sine theta, which is equivalent to ma of x. If you notice, the masses are the same, so we can cancel them out, and that gives us m will cancel, ax is given as g sine theta. So whenever an object slides down a smooth inclined plane, the acceleration will always be given as g sine theta, and that's the derivation. When an object slides down an inclined plane, which is very, very smooth, meaning no friction acting, no friction present, the acceleration will always be g sine theta, where g is just the gravity and sine theta is the angle at which, you know, the plane makes with the horizontal. We move on to case 2 and see what the difference is going to be. Case 2, we are told the object slides down with an acceleration ax, but then the plane is rough. The plane is rough, and then the object slides down the plane. So if it slides down the plane, it means there will be two forces acting. Mg of x will be present. In this case, mg of x will act in that direction because the object is sliding down, and mg of x is given as the sliding force here. That's the force acting, but then the object is sliding down a rough plane. It means friction is also present, and that's going to be the direction of friction, Fk. So we are going to solve for f of y. We know the y-axis, the acceleration will be 0, and that gives us Fn equivalent to mg cosine of theta. So that wouldn't change much. We move to the x-axis. What are the forces acting? The forces are mg of x, which is positive. You just have to watch the arrowhead. The arrow points to the right, and that means the force is positive. And look at the other force. The frictional force is against the motion of the block, and that has to be a negative force. So we know sum of forces in the x-axis is equivalent to ma of x. What are the forces in the x-axis? We saw something like mg of x minus f of k is equivalent to ma of x. Recall that Fk is given as mu Fn, and we found Fn to be mg sine theta. Therefore, Fk will be mu mg cosine of theta. If all of these are substituted here, we will have mg of x, which is mg sine theta. Mg of x is mg sine theta minus f of k, which is mu mg cosine of theta, is equivalent to ma of x. Where is common? M is common. And that gives us m. On this side, g is also common. So this will be mg into sine theta minus g is already factored out. Mu is there times cosine of theta is equivalent to ma of x. M is on both sides of the equation, so we can eliminate that. And m cancels m. This gives us, I think this part can be eliminated again. This gives us the acceleration ax is equivalent to g into sine theta minus mu cosine of theta. Clear? Good. You will notice that the total acceleration is just the difference in acceleration. That is the acceleration of the smooth part minus the acceleration of the rough part. And this can be a of x is equivalent to g sine theta minus g mu cosine theta. G sine theta, we are told, is the acceleration on a smooth surface, and this is just the rough surface will be given as this total acceleration. Is that understood? Good.
Yes.
We move on. These are all things that I've explained, but you can go through them to understand it better. Good. We are given a first problem. It says a block is being pulled down a rough incline as shown below. Draw all the forces acting on the block. One key thing you need to note is that the plane is not smooth, but it is rough. And that tells us friction is present. So we are not going to ignore friction, and you should know the direction in which the block slides. In this case, it is sliding down the plane. So that's the direction of acceleration. It is already drawn for you. All you need to do is to draw the forces acting. You should know that the friction force is present, the normal force must be there, and the gravitational force must be resolved into x and y. I'm not going to do that for you, but then I can display the answer for you to verify. There's the normal force, mg of y, which you have to resolve into x and y components, F of friction, because the block is sliding down, friction must be in the opposite direction. Good. These are things that I've explained. So you just need them for your own personal benefit. Okay, question 2. Given an inclined plane that makes an angle of 32 degrees with the horizontal and a box of 5.8 kg, what is the component of the gravitational force along the inclined plane? What are we asked to do? Is it the normal force we are asked to solve? No. The normal force, no. But then the component of the gravitational force along the inclined plane. This tells us what the component of G, which is horizontal. That is mg of x in other words. That is what you are asked to solve. I've already displayed the formula before, so I will just display the answer. You see, mg of x will always be mg sine theta, where m and g are constant. They are already given. Theta is the angle, which is 32. Okay, the same question, but here we are asked to calculate the magnitude of the force into the plane. The magnitude of the force that goes into the plane is the same as the magnitude of the force, or the magnitude of the gravitational force, which is perpendicular to the plane. That is mg of y. If mg of x is mg sine theta, it's obvious that mg of x will be mg cosine of theta. And the answer should be, I don't know, but you can just check for yourself. It's there. Putting it all together, let's just look for a problem. This is what I was explaining. The surface is smooth. The acceleration will always be g sine theta. Good. What is the x component of the gravitational force? We've done something like that before. Is a similar problem. Good. Let's try this together. Determine the value of Fn. Determine the value of Fn and the x and y components of the gravitational force, given that m is 20 kg and the angle is 40 degrees. We are required to answer 3 questions or to solve 3 problems here. The first one says the Fn, we determine the magnitude of Fn. Determine the magnitude of Fn. We don't know, so we give it a question mark. What else? And the x and y component of the gravitational force. That is mg of x and also mg of y. Given that the mass is 20 kg, gravity is 9.8 or 10 meters per second squared, and the angle theta is 40 degrees. It's an inclined plane. We have to draw it. They've already drawn the diagram for us. So you do the math and obtain your answer. We know Fn, the forces acting on the y-axis are Fn minus mg of y, which is equivalent to 0. There is no acceleration on that axis. And that will be Fn is equivalent to mg of cosine of theta. We know Fn, we know mass, gravity, cosine of theta. You substitute into the equation and obtain that. That is for Fn. We know mg of y to be equivalent to mg cosine of theta, and mg of x to be mg sine theta. So these are the 3 equations needed to obtain this question. This is 1, 2, 3. I guess you will be good. Okay. Another problem. A block of mass 5 kg slides down a frictionless incline at an angle of 30 degrees. Draw a free body diagram and find its acceleration. We are told that the block is frictionless, and that means there is no friction acting on the object. the mass is given, and the angle of inclination is also given. All we are required to do is to draw a free body diagram showing all the forces acting on the block. The block slides down, so that's the direction of acceleration. That's the mass. You have Fn acting, mg of y, this is mg of x, and that's the direction of acceleration. What are the forces acting? It's the acceleration that is required. So we don't have any business with the y forces, because then acceleration is required. The block, or how to call it, the plane is also frictionless, so we don't need anything to do with the y forces. So we go straight and write F, sum of F in the x-axis is equivalent to ma of x. What are the forces acting? It is only mg of x. So that gives us mg of x is equivalent to ma of x. I don't want you to cram. If not, I would have directed you to use the equation a equals to g sine theta. But let's see what this is going to yield. We have mg sine theta is equivalent to ma of x. M cancels m, and ax becomes g sine theta. G is 10 in this case. Is that, yeah, that's what we are given. Sine theta, which is 30, and sine 30 is just 0.5. 0.5 by 10, that should be 5 meters per second. So you see how such questions are solved. We've dealt with this already. Okay, now you can recap, or you can just compare the equation we obtained before to what is given here. When the surface is rough, as I said earlier on, the acceleration will be g into sine theta minus mu cos theta. That is what they've already derived for you. But you don't need to cram. As a student, you wouldn't cram. Just know what you are doing, and then the rest will be easy. Okay. That's it. Good. Good. We've dealt with all of this. Let's take this problem. It's a bit different from what we've been doing. It says a 5 kilogram block slides down an inclined plane, and the angle is 30 degrees. But then the special case is that the object moves with a constant speed. And I believe you know when an object moves with a constant speed, the acceleration will be 0. That's the first thing you've noticed in that question. The acceleration will be 0 because the speed is constant. And then we are asked to draw a free body diagram and also to calculate the magnitude of the coefficient of kinetic friction between the block and the plane. I will solve that one for you, but no special case is required here. We will draw the block. That's theta, which is 30 degrees. The object slides down, but then A is 0. This is because V is constant. What are the forces acting? The normal force. What else? Gravitational force, which should be resolved into x and y components. This is mg of x. Did I do that right? No, mg of y, and this would be mg of x. Good. If you recall from one-dimensional, dynamics, we are told that the frictional force is always given as mu times Fn. But since this is one-dimensional force, Fn will be mg. Therefore, F will be equivalent to mu times mg, and mu, which is the coefficient of kinetic friction, will be F, the frictional force, all over mg. Well, there will be a little bit of variation here, because we are dealing with angles, and then it has to be captured. Nothing will be ignored here. You follow the steps that I taught you. You resolve the forces into x and y components. Let's deal with the y component. We know sum of F in the y-axis will be 0, and that will be Fn minus mg of y is equivalent to 0. And that simply tells us Fn will be equivalent to mg of y, but then mg of y is just mg cosine of theta. And the forces in the x-axis will be equivalent to ma of x. What are the forces acting? What are the forces acting? It is mg of x, which is sliding the block down, and frictional force, which is trying to oppose the force. So that gives us mg of x minus Fk, which is the frictional force, is equivalent to ma of x. We substitute mg of x as mg sine theta minus mu k. Fk is the same as mu times Fn, which is equivalent to ma of x. But then the question says the object or the block slides with a constant velocity. And we know when that happens, a will always be 0. This gives us mg sine theta minus mu Fn is equivalent to 0 times ma, which is 0. And that will be mg of sine theta is equivalent to mu times Fn, where Fn was obtained as mg cosine of theta. So we substitute that into the equation, and it will be mg sine theta is equivalent to mu times Fn, where Fn, you got the diagram already, so I can clean it. Mu times Fn, where Fn is mg cosine of theta. Can we make mu the subject? Yes, we do, by dividing everything by mg cosine of theta. And this gives us mg sine theta all over mg cosine of theta is equivalent to mu. And when simplified, it becomes sine theta all over cosine of theta. Mu is equivalent to the mg will cancel. We are left with sine theta all over cosine of theta. And from the study of trigonometry, we know sine theta over cosine of theta will always give us tan theta. So in short, mu is just given as tan times the angle of inclination. But then let's look at the question. What is given? The angle is given, isn't it? Yeah, we can solve for mu. So mu will be tan of theta, which is 30. Tan 30 will be, let's punch it together and see. Tan 30 is 0.577, which is the same as 0.588. As I said earlier on, it has no unit because it is a dimensionless quantity. So that's the answer. C is the correct option. So you need the same explanation to answer this particular problem. We are given the angle and the coefficient of kinetic friction or static friction is required. We do the same thing. Mu s will be equivalent to tan theta. Theta is known. So you just substitute and obtain your answer.